All right, announcement before we get started. Exam on Friday. We've covered enough to go over an exam. Study period Thursday. I will spend the class going over examples of things and answering your questions. I have a few examples prepared of some of the more difficult concepts, but if you'd like me to prepare any other examples of any other concepts, please let me know ahead of the start of class. Because as you can imagine, coming up with good pumping lemmas and good pumping lemma questions that are approximately the difficulty of the exam, that aren't exactly on the exam, aren't exactly on the homeworks, and have the same outcomes are difficult to create on the spot. What else? I think that's about it. You have an assignment that's due a week from Wednesday, so don't worry about that assignment for the moment. Prioritize the exam over the assignment. And I just revealed the first of probably 2 project ideas. And you will have to do 1 project. I took a quick glance and it looks like we're probably slightly on pace to have about a week and a half for the second project idea. I can try to reveal it a little bit earlier in case you want to do the research on something that is an actual parsing algorithm for compilers. But I want to show you what your first project idea actually was. So here is the assignment itself. It is to implement the CYK algorithm. So you can see, if you take a look at input.txt, this is the type of input we are going to be looking for. And of course, this is Canvas, so it'll take about 8 years to load this. Not joking. Hey, load to the top. All right. So here's an example of what the input file will look like. The first number you see at the top of the file is the number of grammars. So you will parse this first number and say, all right, what follows is going to be 3 grammars. Then there's a blank line, and then there are a bunch of productions that relate to the first grammar. So you see that there are no ors. You don't have to parse the vertical bar symbol. All productions will be on a separate line. They will adhere to CNF, so you can expect that this is a CNF grammar with legal rules. What follows from the grammar is a blank line followed by the number of query strings for this grammar. So there are 2 query strings associated with the first of 3 grammars, BAABA and BAABB. The question is, are either, neither, or both of those query strings in the language defined by the above grammar? Then you will see the second of 3 grammars, followed by a number, followed by some query strings for that grammar. Now there are 3 query strings for the second grammar. And then there is 1 query string for the third grammar. Question?
We're gonna code this at some point.
That is what this assignment is you're going to be writing the CYK algorithm to convert this input into an associated output text file with that. So yeah, this is the project for the class.
Do you care about the language that we use or not?
It depends on whether or not the TA can run it. So I would say languages you can use, Java, Python. If it's something other than those 2, let me know, and I'm sure it's something that can be, it's easy enough. I would say C# is probably fine.
So no assembly.
You hate yourself? I want you to be successful.
Right.
If you really wanted to challenge yourself and do it, I'd talk to you first, but I'd probably say yes if there was a real outcome or really wanted to do it.
Trust me, I know.
So this is my example file for input. So this just goes over everything that I just said in textual form. So input, these are the associated rules, and then this is the output file that you should produce given that input file. So we load this. And Canvas is suddenly faster now. I want you to reprint the grammars because we want to be able to see the grammar, and then we want to be able to determine whether the strings were in the language or not in the language. So reprint the string, and then you will either follow that with is in the language defined by the above grammar, or is not in the language defined by the above grammar. So you're just answering the CYK question, membership question. And part of the outcome for this is that you do code it using dynamic programming. Your solution should be cubic with respect to the input, so answering that question should be cubic in the size of the grammar. And the length of the string. So grading for it, 70 points for your implementation. You get 0 out of 70 if it doesn't compile, and you get 0 out of 70 if it doesn't have cubic time complexity. So you'll want to absolutely verify that both of those things are true. If you have questions about this, you can certainly ask me before you get started. Run some ideas by me. I'd be happy to take a look at your ideas and make sure it adheres to those two requirements, because I do not want to be giving anybody a 0 out of 70 for one of those reasons. But it's just to make sure that you are having that dialogue with me. You're not running with some assumptions and then coming back to me with something that is brute force or is not going to run for reasonably length strings. The idea is to produce something that is useful and relevant. In every class that I teach, I want the programming outcomes for that class to be something that you can put in your code portfolio that you can show to prospective employers. And I think that there's a lot to talk about with this project. You can talk about the application to compilers. You can talk about the analysis of the complexity. You can talk about how it's an implementation of dynamic programming, what that means, and how this solution adheres to the dynamic programming principles. So I would think that this would be very useful to have for prospective employers, but that's basically the idea. It's not crazy long beyond that, and I also said that rather than do the Google yourself, I don't care if you use outside resources to check your work. If you go to this link is a CYK visualizer. Here is an example grammar. Note that the arrow here is different from my arrow, so you can't quite just copy and paste. I do this on purpose, just in case you were able to scrape some code somewhere. I will be checking for that, but I also don't want you to be able to just run with it. You can see that this is step by step, very similar to what I drew, just kind of inverted. And if you go step by step, you will see the different productions that get added, as well as the references. What cells are they referring to come up with that answer? So that visualizer can help you with the associated logic for answering that question. And again, if you get the S in that last box, then the answer is yes. So here is the grammar. Here is the query string, and you can see that regardless of what you put in, it will solve it and show you the work.
And you don't want code to display that whole pyramid thing?
No. Nope, I just care about the output text file. You do not need a visualizer. If you'd like to, I don't think this is a crazy extra step, and I think that it would be really useful to prospective employers to show your GUI work. That said, not a requirement for the class. I care more about the algorithmic details than I care about the visuals. But yes, use this site on the examples to start to think about how does this algorithm work? How does this work? Questions on the assignment? I like to think that the idea is pretty straightforward, but the actual code implementation might be a bit more challenging. So my recommendation is to get started early and come to me with questions, because we have over a month left in the quarter to work on this. Don't wait until the last week. Get started early, get stuck early, and I am happy to help you to whatever extent that I can, so that the end result from this is something that you are very proud of and really want to show off. Okay, let's dig into what we were talking about last time. I just close the file. I did, that's really fun. Touchpads, right?
Our NPDA is gonna be on the exam.
Let's see, were they on the study guide? Anything that's on the study guide is legal for the exam, so if you're curious about this, you just go over to modules. Scroll down to study guides, you can even see that I have a couple of study guides that I'll be modifying before I release them, but they're at least last time's study guides. But you go into the exam 2 study guide and you should see that regular grammars. Did regular grammars go first? It should be regular expressions, right? So I may have made a mistake there. Pumping lemma, context-free grammars, and push down automata in the form of an NPDA. Yeah, it looks like this is gonna be tough because the assignment that's going to be due the week after the exam does have this material. I don't like doing that, but I also feel like if we only have it over context-free grammars, the pumping lemma, and regular expressions, then there's not much that I can ask there, and knowing how much there is in the last 2, I think that makes the most sense. I can give you plentiful examples of them over the next few days and during our Thursday review session to hopefully help that process. But let me know if any part of that feels like I haven't done enough examples, you don't have a good understanding of something, or if you want some feedback on a homework problem or 2, I can go through that with you during office hours to make sure that you are as confident in it as possible. Good question. All right, we left off with this example. So we were trying to figure out how to represent WWR with an NPDA. Is that right? That right, or is that the one before that we were?
I think that was the one before.
I thought so too. Yeah, we had that, right? No, that was the one we were working on, pretty sure. We did. Yeah, we did this one last time. So AB star, number of A's equals number of B's. Did we go over the WWR? Because I thought,
I think you remember WWR. I have it in my notes here. Lots of closure.
so we needed to know where the middle of the string was. Maybe we did. Yeah, I remember we did, and then I was not seeing what Nathan was saying with regards to how to make the middle better. Yeah, now I remember. The weekend was a long one. It felt like a long. Okay, did anyone have any questions about this? I don't think I revealed this slide. We ended with the diagram. But these are the rules, and I like to think of NPDAs. You can either draw them out, but they start to get a little bit messy. I ended the class with the diagram saying, if I showed this to you without telling you what the language is, could you tell me what the language was that it accepts? And there were a lot of, I don't know about that, that's pretty confusing, this doesn't really show that well. And then I said that kind of like assembly instructions, sometimes it makes more sense to give some general groupings for these rules, and then listing the rules associated with those ideas, because these groupings don't appear in the NPDA diagram really, there has to be some kind of, you have to look at the state to say, all right, the state is all about pushing W onto the stack. This state is all about popping W off the stack and matching it to something from before. So this to me is much more useful algorithmically for looking at some of the NPDA rules. So neither one is more correct, but you may see them in either of these forms, just to be able to. Different ones will make more sense or more or less sense, given what you're trying to describe or show. Questions on drawing NPDAs? Such a quiet class. All right, the next thing we're gonna cover then is an algorithm for converting a context-free grammar to a non-deterministic pushdown automata. What do we know going in? Given the context-free language, we know there is some NPDA that accepts it. But to be able to show this idea, we need to derive an algorithm that converts a grammar into an automata. It turns out that this process is significantly easier if we assume that the grammar is in Greibach normal form. We said we wouldn't talk too much about exactly what Greibach normal form is, but here is one of the places where it is used, is in this conversion algorithm. So remember that Greibach normal form is just we have a single terminal followed by 0 or more non-terminals. So if the grammar is not in Greibach normal form, we have to first convert it. Don't worry about that. That's not part of the intended curriculum here. But you can assume that if you get a grammar for this, a problem of this type of conversion, that it will be in GNF. We then proceed with a leftmost derivation for every production. What this tells us is the transitions in the NPDA, which makes sense because there's only a single terminal that says when we move from this state to that state, we're going to consume that terminal that is the first terminal in GNF. Let's take a look at what that means. So construct a pushdown automata accepts the language generated by a grammar with the following productions. We'll use a very simple grammar to start with. Note this grammar is not in GNF. Any problem that I give you will be in GNF, but if it's not in GNF, just in general, then you will need to convert it. So here is the conversion after it is done. So every production is a non-terminal arrow, a single terminal followed by 0 or more non-terminals. And that is true for each of those productions. When we take this grammar and we try to produce any string that might be in the language that is described by it, we have to start with the start symbol. So we push the start symbol onto the stack. We're going to start seeing that what we push onto the stack and pop off of the stack is in fact not these arbitrary symbols that we've been drawing in our NPDAs so far, but are in fact non-terminals in a grammar. If we want to do the conversion, the stack is going to contain these non-terminals that we need to resolve or evaluate to be able to attempt to derive that string. Or rather to make the NVDA. So we can't stay in the start state, we only want to have this happen once. So what does this look like? A move from Q0, popping off the bottom of stack character, is going to move into a new state and is going to push the start symbol onto the stack. So we do not want to loop back to Q0. Q0's only purpose in an NPDA that is generated for a context-free grammar is to add the start non-terminal to the stack. Because every string is going to start with that start non-terminal. So every path through this NPDA is going to start with that start non-terminal being evaluated into something. There's an equivalence between those two. And again, I apologize for not doing my subscripts correctly here. Apparently, I did not look at this ahead of giving it. Those should be Q sub 0 and Q sub. I think I've done that a few times this quarter. We can look at all productions defined by this non-terminal symbol, and we need to make a transition rule for each of them. Right? Because if we pop this S, we can replace this S with one of these two rules. So we need a transition out of this state, Q1, when we pop this S, because it's the only thing that can be on the stack going into state Q1, we need two possible transitions out of that adhere to these two rules. That's the only thing we can do from an S. So S arrow lowercase a capital S capital A, we're going to read an A from the input, so that becomes the edge label. Transitioning on an A in the string, popping S from the stack. So you're going to pop the left side, and you're going to push the right side of all non-terminals that come after the terminal that begins this. So the A becomes the edge label, the SA becomes what you push onto the stack. Note that it's in the opposite order though. You want to push the A followed by the S, because you want the S to be on top. Because in any derivation here, we have to resolve the A, because we're doing this left to right. We're doing a leftmost derivation. So we need to resolve this S before we resolve this A. So A, S. But this becomes why we write them the way that we do. If you've noticed that when we're pushing things onto the stack and we're reading it in NPDA form, we start by pushing the character on the right and then move to the left, and the left became the top. This is the reason for that. Because in a grammar, we're going to start pushing at the right and end pushing at the left. It maps directly to the non-terminals of the grammar that you would be reading from. Note that S arrow A now means we're going to read an A from the arrow, the input, pop the S, and push nothing. We can combine these two rules into a single rule where now the input to this is exactly the same. We're starting in state Q1, we're reading an A and popping an S. That's true for both of these rules. So we can combine these two rules, these two destinations, into a set that says we can loop to Q1 and push SA, or we can loop to Q1 and push nothing. So two rules in one rule, just combine them into a set if the left-hand side of that rule is the same, which in this case it is. Moving on. The next rule says capital A arrow lowercase b capital B. We can make this transition The idea is we're going to now read a B from the input string, pop an A, push a B. That's how we would read this rule. So we're gonna write that rule as moving from state Q1 to state Q1. We're going to read a B, pop an A, push a B. Questions on either of these rules so far? Why we're doing what we're doing, how that ties into the grammar, how this is represented visually in an NPDA? Last rule was capital B, arrow lowercase b. We're going to read a B, pop a B, push nothing. Note that we're still moving from Q1 to Q1. Read a B, pop a B, push nothing. In general, all you should do is just continue this process for every single production. Why aren't we ever moving to some other Q2, Q3, Q4? We're always looping back around to Q1. Why is that?
So we've already set in stone from the beginning.
Yeah, kind of the state tells us what has to be on top of the stack. If we go back and look at the grammar. This is the conditional here, what happens to be on top of the stack. If there were multiple different subgrammars where we wanted to say, are you in this subgrammar or that subgrammar? Maybe then we'd have two different states. But we'd have to be reusing these labels, these names. Since it's an NPDA, we can make two different transitions out of the same state, consuming the same character, as long as there is some difference in what happens to the stack. Which is guaranteed when you have two different rules. You're not gonna have S arrow lowercase a or lowercase a. That's the same rule, so of course the transition would be the same. Yeah,
So since example, turn the CFG into the NPDA, we change it to a PDA, is that a mistake, or are we just making a PDA?
this is, so yeah, it should be an NPDA because that's what we're doing, but in general, it's just a pushdown automata. A non-deterministic pushdown automata is a type of pushdown automata, but yeah, this will be an NP. It's an NPDA because we have these two A's here. We read an A, we can take one of two different transitions, and to be a deterministic pushdown automata, we have to be able to explore this space and know which one is correct. But an NPDA says you're free to do both simultaneously at the same time, as long as we can reach an accepting state, we will do so. Even if only one path out of 80 billion is an accepting state, we accept. Excellent clarification. So that is the general process. After we've done every production, we need a final transition to head to a final state. So if the stack is empty, transition to an accepting state. And so we can do it like this. We say going from Q1, reading nothing from the input and popping the bottom of stack character. Then we go to Q2 and push nothing. Now notice that suddenly we're using the form where we're accepting an empty stack. We can't even have the bottom of stack character on. But if we wanted to put that bottom of stack character back on, this lambda would just become the Z. But we can only make that transition when we have no more non-terminals left to parse, for lack of a better term. How does this feel logically? Does this, or intuitively, does this intuitively make sense for how now a state machine is the same as a grammar? Or how to think of the grammar now as a state machine?
forward, kind of.
Yeah, the process itself isn't too algorithmically difficult. But I think it's really important to draw these intuitive connections between these, because otherwise they just seem like completely distinct ideas. And if they're distinct ideas, then they represent the same thing. You just have to memorize it rather than having that intuition. And wherever you can have that intuition, that helps to have a bird's eye view down at the whole concept and say, oh, that whole concept is really the same thing. Just different ways of expressing the same idea. So some quick notes. All logic involving consuming characters in the input happens in state Q1, which means that for any grammar, this is really only 3 states. Regardless of the complexity of the grammar, there are only going to be 3 states in the associated NPDA from converting that grammar. Even if there are a million productions, that just means there's going to be a million out edges from state Q1. Don't try to draw that out. That's going to be a nightmare. So because of all the transitions, it's difficult to draw it, it's difficult to visualize it. So this is why we write them with a list of transitions, rather than trying to draw it out, especially when you're doing a CFG to NPDA translation. All right, here's the grammar. First thing to ask, is it in GNF? Now there's a test bar. It is in GNF, so go ahead and draw an NPDA that accepts it. If you rather not draw it, you can write out the transition rules, because how many out edges are there going to be from that state Q1? Five. We would have 1, 2, 3, 4, 5, 6. Number of productions in the grammar would be the number of out edges from Q1. That's kind of gross. But I've drawn 6 on the board. It is possible. 3 on top, 3 on the bottom. So how many states will that NPDA have? 3. They all have 3. So go ahead and draw out that initial state transition rule to start, just to make sure you're on the same page. What is that initial state transition rule? Go ahead and work on that, and then I'll reveal the answer to that before we move forward. Anyone think they have that initial transition rule?
Same as the last one.
It is the same as the last one. In fact, this will always be the same. Any grammar with initial production S arrow something, you just gotta put the S on the stack. Go ahead and write those 6 transition rules for the middle state. We have those 6 transition rules. Get close. There they are, so you can check your work. You can group lines 2 and 3 together, I just didn't have the. Room in a line, or I guess the book didn't, but.
Would you group 2 and 3
Yeah,
together?
no, you will, because they consume a separate character. Oh, okay. Yeah, whenever these are the same. You can't combine all 3 of these, you can combine these 2, because they both consume the A, the B is separate. Yeah. So, 6 rules, 5 lines. Acceptance to the final transition state, the final transition to the final state. English is part of this morning, apparently. But yeah, it is a Monday. There's that final transition. You can call this Q2, QF, whatever you want here, it doesn't actually matter what it's named. But in general, you can. Since these are only gonna be 3 states, naming this something that shows that it is the final state could be something that improves the readability of. This. So starting in Q1, consuming no character, popping the. Bottom of stack character, you end up in the final state, and. Now we have the book making no sense, because now it pushes back on the bottom of stack character. So this is why I say it doesn't really matter. The book kind of contradicts itself with regards to whether that bottom of stack character is there or not. Please be consistent though. Don't have some problems in a homework have it, and some problems in your homework not have it. What about going the other way? If we take as input a pushdown automata and want to create a grammar for it, how could we do that? Well, it's the exact opposite process. So this becomes very interesting. Because the resulting grammar that you get from this is in GNF. So the stacks represent all unexpanded non-terminals. We're gonna make a couple of assumptions. We need a single final state that can only be entered if the stack is empty. If that's not the case, then we need to do some work with the NPDA to get it into an equivalent form that has that. We won't discuss how to do that, so we're making this assumption. There is a way to do it. Each move is either going to increase or decrease the stack count by 1, rather than pushing multiple symbols or popping multiple symbols off the stack. And of course, any NPDA can be converted to an equivalent one where both these assumptions are met. We won't go over that exact process because time, but you can find that in the textbook if you're curious exactly what that process is. So we're not gonna go over this exact transformation, but it's useful. It's quick, it's the exact opposite of the process we just went through. So feel free to look into that. We can also come back to this if people are curious at the end of the course and we have some time. So everything we've talked about with regards to pushdown automata has been non-deterministic in nature. Why haven't we talked about determinism? Does anyone have any guess as to why we haven't talked about determinism in the PDA world? It definitely is more complicated. To start thinking about that. How would you go about converting an NPDA into what we're gonna call a DPDA, a deterministic pushdown automata? Any thoughts on this? What restrictions do we need?
You only have one transition from it,
Yes, that's true of a DFA over an NFA, right? You could only have one out edge that consumed a particular character in the finite automata world. In the PDA world, it's a little bit different. Now, instead of there just being worrying about a single character in the string, now we need a tuple of a character in a string and top of stack character. At most, one move can be made given that tuple. As soon as you have an A in the string and a capital S on top of the stack, or an A in the string and a capital A on top of the stack, those are two distinct moves. And they're both legal in a DPDA. So think of them now as a tuple. You have on the left-hand side, you have a tuple, and on the right-hand side, you have a single out edge to that state, representing that tuple. Input symbol, top of the stack character. Of course, that means that lambda transitions are still possible, as long as an operation is done to the stack. You cannot have a lambda transition that does not read an input character and does not make a change to the stack. But you could do one or the other of those. You can have a legal transition that doesn't consume an input character but makes a stack operation. Or one that consumes an input character and does not make a stack operation. Either of those are fine. There's one additional rule here, though, that says if a lambda transition is possible for some configuration, no alternative that does consume an input character is available. What does that mean? We can't have two rules that says something like from state Q1, we move to state Q2, consuming no input and making no operation to the stack. You could not also have an out edge that says we don't consume an input character and we do consume an input character at all. So why do we still allow lambda transitions? So top of the stack, of course, we can't allow a lambda transition with no associated stack change, but it means that if we do allow a lambda transition with a stack change, we can't allow another one. The way that I prefer to think about determinism at all times, at most one possible move exists. Given your input, given the state of this system, but now the state of the system is more complicated. The state of the system is what state you are in and the stack contents. And we can only visualize the top of stack character. We can't dig into the stack. We can only look at the top of stack character. So your state is now the state that you're in and the character that is on top of the stack. So given that you are there, and given that you are looking at the next character in the input string, only one move can exist. If you write or if you draw a DPDA and you find yourself in a position where you have options, I can either go there or there, then you do not have a DPDA, you have an NPDA. So given any state, there's only one possible move. So in regular languages, we could freely convert between DFAs and NFAs because they represented the same language. there is no such conversion for context-free languages. There are some non-deterministic context-free languages, which means that there is no such DPDA that represents that language. So that means that the languages that have associated DPDAs is a different class of language than those who have NPDAs. And in fact, it's a smaller class of languages. I'm just gonna draw this out real quick. We'll get a bigger version of this later in the course, but I guess let's try to draw it here. So we have regular languages that are DFAs and NFAs. Outside of this, there is another class of language that is the DPDA language, and outside of this, there's another class of languages for NPDAs. This tells us that if you can draw a DFA, you can also draw a DPDA, which makes sense. If you can draw a DPDA for a language, you can draw an NPDA for that language, but it doesn't work the other way. There are some languages out in this space where we can draw an NPDA for it, but no such DPDA exists. No such DFA or NFA exists. So to prove that a language was outside of this circle, we did the pumping lemma. This says that to prove that this language is not in here, pumping lemma. To prove that a language is in here, you would draw an NPDA. But this is also the context-free grammar. That tells us that not every context-free grammar has an associated DPDA. So the reason we didn't talk about it is they're actually separate classes of languages. So that's kind of wild. Race will go away over there. I'm not gonna walk all the way over there. Who has time for that? So we're gonna expand that diagram later on in this course as we talk about more and more classes of languages, but that's why we haven't talked about determinism so far in this talk, is it just doesn't really matter or make sense. It doesn't convert directly to everything that we've been talking about. So only some NPDAs have an equivalent DPDA, and we're out of time, so we're going to come back tomorrow and give you some examples of DPDAs, and as well as some languages that don't have an associated DPDA to try to get at why aren't these equivalent. Try to understand intuitively, given an NPDA, why can't we just convert it into a DPDA, or what kinds of languages have that restriction? All right, we'll do that tomorrow. I have office hours starting now. If you have any questions about anything really, project, the homework, the upcoming exam.
The project due the final day or the last day of the quarter?
I think it's the last day of classes in the quarter rather than because I need to give the TA some time to grade it. If I make it the end of finals, then he basically has the weekend before grades due. So I think I'll be willing to work with people individually if you have a really hectic schedule at the end of it. Maybe one or two people can request extensions, and that way the grader can get started grading things. But I can't make the deadline later for everybody because yeah, too much on our full grader. His sanity is important to me. I need him next quarter.
Thank you.
See you later. Thanks, everyone.